The binomial theorem is a theorem that's going to allow us to multiply higher order polynomials very quickly. We have not talked about polynomials in a minute because we talked about polynomials for a while, then we had rationals, logarithms, conics, series, and sequences, but now we're back to polynomials. Feels weird, but I promise it will tie in. Couple of definitions we need. A factorial. Have you ever heard of a factorial before? A factorial is, in mathematics, the symbol exclamation point. That's a mathematical symbol, believe it or not. The symbol exclamation point indicates a factorial, which is the product of all positive integers less than or equal to a number. Okay? A factorial is simply just, like if we had 5 factorial, which we do right there, it is just 5 times 4 times 3 times 2 times 1. It is the product of all positive integers less than or equal to that number. So 5 times 4 times 3 times 2 times 1. What is 5 times 4 times 3 times 2 times 1? Bless you.
120.
120. Great. Now, in your calculator, there is a factorial button. I don't know if you've ever noticed it. Press math. I'm trying to do this off memory. Go over to number. Nope. Go over to the probability PRB. So it's on math. You're going to go over to, it's the probability tab, PRB. It's the 4th option on the math screen. And then it's like, I think it's like the 4th option there. Is that correct? Yes. Option 4 says factorial. So you'll have to type the number in first. So if you're wanting to do 5 factorial in your calculator, you'd type 5, then go to find the factorial button. But it's on the probability screen because it's used a lot in probability. So because we don't want to sit here and literally do 9 times 8 times 7 times 6, because the number could get really, really big, can y'all do 9 factorial in your calculator? Just make sure we got it. 362,880. It's multiplying numbers, so these numbers should get big really, really fast. That's a factorial. And the reason we're introducing factorials is because they're used in what are called combinations, which will also come together. Combinations is a probability idea of combining discrete numbers. If j and n are integers, so just some random numbers, j and n, some integers, making sure that n is bigger than j, but they're both positive, that's what that says, then the symbol n over j, so n choose j is how you would say that, n choose j, is defined as n factorial over j factorial times n minus j factorial. So we have factorials inside the combinations of n choose j. Okay, what a combination is it's just telling you to literally combine the things together. So if we had, in the first example, 3 things, and I want you to choose one of them, how many options do you have to choose just one thing out of 3 things? Don't think about it too hard. 3, okay. Let's prove that with this formula. The formula 3 choose 1 would be 3 factorial over 1 factorial times 3 minus 2 factorial. 3 factorial is 3 times 2 times 1. What's 3 times 2 times 1? 6. And then I have 1 factorial. Sorry, where did that 2 come from? This should be a 1. Y'all got to stop me when I'm being crazy. What is 1 factorial? 1. 3 minus 1 is 2. And 2 factorial would be 2 times 1, which is 2. 1 times 2 is 2. 6 divided by 2 is 3. Now what this means in real life, if we're actually choosing these things, let's say I have 3 objects, A, B, and C. I want you to choose just one of them. Your options would be choosing A, choosing B, or choosing C. That's it. You're like, duh. Okay, let's go to B then. If you have 4 objects and I want you to choose 2 of them, how many options do you have to choose 2 things out of 4 things? Let's see. Okay, so let's say I have 4 things. I have A, B, C, and D. I want you to choose 2 of them. I could choose A and B. I could choose A and C. I could choose A and D. What else could I choose? Oh, can't not double up on the things. B and C. What else? B and D. What else? C and D. Now, this is not a permutation. Permutations are the ones where order matters, where you could do A and B and B and A. We're just like, pick 2 things. I pick these things. They're the 2 things I picked. The order that I picked them does not matter. This is just combining them in a certain way. When the order matters, that's called a permutation. This is just a combination. So we know, how many did we find? Is that all of them?
16.
We found 6. So let's use the formula and make sure that makes sense. That's a permutation, not a combination. So we would have 4 factorial over 2 factorial times 4 minus 2 factorial. Thank you, Trey. Okay, now this one we probably want to use some formulas for. You can throw this directly into a calculator since we know where the factorial button is, or these numbers are small enough, we could probably do some of this in our head. 4 factorial is 4 times 3 times 2 times 1. 4 times 3 is 12. 12 times 2 is 24. 2 factorial is 2. 4 minus 2 is 2. 2 factorial is 2. 24 divided by 4 is 6. That's how many we found when we did this combination. We said that there would be 6 options for us to choose from, combining the 2 things without order mattering. That's a permutation. Okay, how about C? C we could probably do in our head. We have 8 things. We want to choose 7 of them. How many options do I have? If we don't want to do it in our head or draw out 8 objects and choose 7 of them over and over again, we can use the formula. 8 factorial over 7 factorial times 8 minus 7 factorial. Now these numbers got a lot bigger. 8 factorial is going to be pretty big. However, doing this in your head is very simple still. 8 factorial is the same thing as saying 8 times 7 factorial. Why is that true?
Because it's the same numbers you just taken off
The first one, right? 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. 8 factorial is just that times 8, right? So I can do this. And then what do you notice is now on top and bottom? They can cancel out the 7 factorials. What's 8 minus 7? 1. So we have 8 divided by 1 factorial, which is just 8. Now when these numbers get bigger, like this last problem, we're not going to want to do it by hand. 65 factorial is going to be ginormic. But if we have 65 items and we're trying to choose 15 of them, we need to know how many combinations or how many different combos or we can make of all of these things. We're going to use our calculator for this one. 65 choose 15 would be 65 factorial times 15 factorial. I don't know why I put that in parentheses. 15 factorial times 65 minus 15 factorial. I'll leave that for you in your calculator. I would make that fancy fraction before I started so that you had the 65 factorial on top. Find the factorial button because you're not going to sit here and do 65 to 1 multiplying them all together. I'll give you a second. Yeah, we should have gotten a really ginormic number. It would say something like 2.0737 e or times 10 to the 14th power. That means we're moving that decimal point 14 times to make this number ginormic. I honestly don't even know how to pronounce that number with 15 digits in it. Now, the reason that we're learning about combinations at all is to use them as part of what's called the binomial theorem. The binomial theorem is going to allow us to expand expressions like x plus 3 raised to the 4th power very quickly. Now, raising something to the 2nd power is easy because that is just x plus 3 times x plus 3. This is saying to do x plus 3 times x plus 3 times x plus 3 times x plus 3. That's a lot of foiling. That's a lot of distributing. That's a lot of places for you to make a small sign error or addition error and mess up the whole problem. Please note, you cannot do this. Please do not do this. I hate it so much. What did I just do that's wrong? Yeah, you cannot distribute this exponent when this is a binomial. The only time you can distribute the exponent inside the parentheses is if it's a monomial, one term. We have two terms. Don't do this. When I was growing up doing math, when you made mistakes like this, the teachers used to call it killing cats because it was such a mistake that every time you did that, a cat died. Don't kill cats, okay? Don't do this. Do this. Thank you. Okay, great. So I don't think that we want to sit here and multiply out that blue equation over and over again because that would probably take a good sheet of paper to do. So instead, mathematicians have found what's called the binomial theorem. What do you notice is in the binomial theorem? Sigma. That's our series that we just learned about. This is why we didn't learn about this with polynomials. We had to learn about series first. This series is saying if you have x plus a raised to some n power, then that n becomes the upper limit of the sigma as well as the top number in my combination and the exponent for n. I am adding up a series starting at 0, ending when that number reaches n. It looks a hot mess. Using it is not a hot mess. Because when we expand out this series and not have it have so much series looking stuff in the sigma, here's what the pattern will look like. The first term in my expansion of a binomial will be n choose 0, which is 1. There's one way you can choose nothing, having 5 things, times x to the n power. The next term will be found if we do n choose 1 option, multiplied by a, which is the term in the parentheses, raised to the x n minus 1 power. This pattern keeps going and going and going until we get to the very last term where there is no longer an x value left. We do n choose n times a raised to the n power. Again, this is a hot mess, but using it won't be a hot mess. The mathematics behind it is crazy cool, but it's kind of confusing. Yeah, kind of. Okay, so what we're going to do is we're going to write this down, and again, for right now, it's not going to make sense to you, but I promise I will make it make sense. You are going to multiply in this pattern to make it easier for you. Something that's called Pascal's triangle, which we'll talk about in a second. Pascal's triangle multiplied by the a value to an increasing exponent number, INC for increasing, times the x to a decreasing exponent power. In my mind, this is what we need to focus on. This is the usable version for someone that doesn't speak mathematics for the binomial theorem. Now, I'm sure you're also asking, well, what the heck is a Pascal's triangle? It's a great question. Pascal's triangle can be useful for finding the coefficients for the binomial theorem. Here's how we build Pascal's triangle. The top of the triangle has a 1. Yay. The second row, outsides have 1. The third row, the outsides still have 1, but the inside is created by adding together the 2 inside numbers. So what's 1 plus 1? 2. That means a 2 is going to go here. On the outside of the next row is 1s, and I create the inside numbers of this triangle by adding up the insides. For this number, what 2 numbers would I be adding? 1 and 2. 1 plus 2 is? What about this next one? 2 and 1, which is? Okay, we're going to keep expanding this Pascal's triangle. 1's on the outside. what should this term be? 4. How about the next one? And then, okay, great. Keep going. We're going to add another row. 1's on the outsides. What's this term? 5. And then, we're going to do one last one. See if you can squeeze it in there. 1's on the outside. What's this number? 6. And then, okay, 15. Great. We have made Pascal's triangle. It's created by adding its like diagonal buddies on each row. Now next to this, because this will be helpful later, you're going to write down some information for me. If you have n equal to 0, Pascal's triangle will be that number. If you have the n value equal to 2, Pascal's triangle, I missed a whole number, equal to 1, Pascal's triangle will be that row. Each row is going to change the coefficients that you use for the power that you're trying to multiply the binomial. So what I mean by that is the exponent of the question that you have. So in the example at the very top, it was x plus 3 to the 4th power. The exponent is 4. We would use the 4th row. N equal to 4 row. It's like the 5th row, I know, because the 1 is 0. So we n equal to 4, we're going to use that row as Pascal's triangle. Again, it's not going to make sense till we start using it, I promise. But this puts all of the information we need on the front of your notes. We're just going to do some practice problems on the insides. Okay. If you open this up, the back of this page is blank because the other page switches directions. If you'd like to rip this off so you can look at the front of this page the whole time, that's fine. Otherwise, we're just going to work really long problems. So I made this a landscape instead of portrait notes. So why would we want to use the binomial theorem at all? This is a simpler example, but I wanted to show you. If I were to expand x plus 3 to the 3rd power, and I did it by hand, I'd have to do FOIL, combine like terms. FOIL, combine like terms. You know how many times the options for me to make a silly like algebraic mistake would happen if I did that, especially if there were negative signs? Lots of chances. When I actually did this by hand, it actually took me like 10 rows because I wrote too big. So it's like you just waste a lot of paper doing this. The binomial theorem allows you to do it much faster, especially when that power is super big. So what's happening here, every time we do this, when we're multiplying this out, we're multiplying by a Pascal's triangle number. Do those numbers look familiar to you? 1, 3, 3, 1. What row on Pascal's triangle is that? The 4th row where it said n equal to 3. Well, look, n is equal to 3. So I'm using Pascal's triangle's numbers on n equal to 3. 1, 3, 3, 1. Great. Then I start with the x for the exponent. It starts at 3, then it goes to 2, then it goes to 1, and then it disappears. So it's decreasing every time. The variable, though, the n, this number right here, is increasing every time. This is 3 to the 0. This is 3 to the 1. This is 3 to the 2. This is 3 to the 3. And then each part of this expansion is its individual piece. My final answer is just 1 times 1 with x cubed next to it. 3 times 3 with x squared. 3 times 9 with x. And 1 times 27 with x. So it allows me to do really, really big problems that I wouldn't want to multiply by hand very quickly, as long as you know the parts of this series that creates the binomial theorem. We are not going to write down this step for almost any of the problems we do. We're going to go straight to this one, because this is the usable version of it. That's a great. So let's try a problem together. Here's some of the things we need to notice when we're doing this problem. First of all, we need to know what power we have, the n power. If n is equal to 6, what's Pascal's triangle numbers that we're going to use? So look at that front page. If n is equal to 6, what are the Pascal triangle numbers? 1. Yep. Do y'all see where they got those numbers from? It's a row of Pascal's triangle where n is equal to 6. Cool. We also have two parts to this equation. We're going to have the x term, or the first term, which is going to decrease in power. And we have the a term, which is going to increase in power as we go on. So if we're putting this together, here's what it might look like. We're doing x plus 2 to the 6th power, which will expand to the first term of Pascal's triangle times x to the largest power it can be, which is 6, times 2 to the smallest power it can be, which is 0. Then you're going to make the next term in this series, because it's a sum of things, with the next term in Pascal's triangle, which is 6. 1 less exponent for x. So what's the new exponent for x? 5, because it's decreasing. And then 2 raised to what power? 1. So decreasing x's, increasing a's. Then we keep going. The next term will be the next number in Pascal's triangle, 15. X to the 4th, 2 to the 2nd. Then we keep going. 20, x to the 3rd, 2 to the 3rd. We keep going. This is 15, x to the 2nd, 2 to the 4th. We keep going. Notice why I turn this sideways, right? These are long problems in the sense that they take a lot of sideways paper. This would be 6, x to the 1, 2 to the 5th, and finally 1, x to the 0, 2 to the 6. Oh boy. Trying to get it to where I can see all of it on one screen. Okay, so that is the expansion, the binomial expansion here. We just need to clean it up. Anything to the 0 power is 1, so you can almost like cross that part out because we're not doing anything with that. It's multiplying by 1 is the same. But all you're going to do is multiply all the numbers together and leave them next to a variable. Meaning, if I were going to simplify this, I'd have x to the 6 times 1, which is just x to the 6. 6 times 2 to the 1, which is 6 times 2, that's 12. 15 times 2 to the 2nd. 2 to the 2nd is 4. 4 times 15 is 60. Then I have 20 times 2 to the 3rd. 2 to the 3rd is 8. 8 times 20 is 160. Then we have 2 to the 4th times 15. 2 to the 4th is 16. 16 times 15 is 240. Then we have 6 times 2 to the 5th. That's 6 times 32, which is 192. And then the very last one, which is the one that the x's to the 0 power, is literally just 2 to the 6th power, which is 64. And that is the condensed or the simplified binomial expansion for x plus 2 to the 6th. We could do it by hand if you want.
I still hate it.
So the pattern is the first thing, the choose number, The reason we did the combinations at the beginning of class, that's Pascal's triangle. So this would be 6 things, choose none. 6 choose none is 1. Then we keep going. 6 choose 1 is 6. 6 choose 2 is 15. On and on and on. That's where the Pascal's triangle number comes in. That's why we had the combinations. The x term, or the first term, starts at the highest power possible, 6, and then just decreases every time. The other one increases every time. The a value, or the second thing, starts at 0 and increases. 0, 1, 2, 3, 4, 5, 6. Every single time you have a term, this is a good check when these problems get long, the exponents should add to the n value. 6 plus 0 is what? 6 plus 0? 6. N is 6. That's good. 5 plus 1? 6. 4 plus 2? 3 plus 3? And on and on. So every time you do this, if the numbers that you're using as the exponents don't add up to the total exponent, something's wrong and we pause. Yes? Let's try another example. Example 3. We're going to expand this expression, 3p plus 2 to the 4th power, using the binomial theorem. Okay. What row on Pascal's triangle am I using this time? 4. So when we look at Pascal's triangle number, n is equal to 4, what are the Pascal triangle numbers? 1, 4, 6, 4, 1. Great. Those are going to be the numbers that start every term. They're my combination numbers. They come from Pascal's triangle, but they're the combination numbers. But this time, do you notice that our first thing is not just simply an x? It's a 3p. So the thing that's going to be decreasing every time is 3p. What's the thing that's going to be increasing every time? 2. Okay, let's put it all together slowly. If we are doing 3p plus 2 raised to the 4th power, each term would start with a number from Pascal's triangle. So this one would start with 1. Then we have the first thing raised to what power? 4. And we have the second thing raised to what power? 0. So the powers have to always total up to 4. Okay, once we get it started, then we just decrease the first one, which I'm writing in black, and increase the one I'm writing in blue. So the next term in this series for the binomial expansion would be 4 times 3p to what power? 3 times 2 to what power?
1.
Okay, cool. Can I let you finish this out? Yeah. Just write it all the way out. I'll help you simplify it, because something different happens this time. Okay, kind of hard to see, because I know I have it small when I show all of it, but did we get the expansion correct? Yeah. Okay, great. Now this time, we can't just multiply the red numbers and the blue numbers, because there's also a value in the in the black numbers. So we're going to have to multiply all of those numbers together. Meaning, for the first term, I want to multiply 1 times 3 to the 4th times 2 to the 0. Well, 2 to the 0, it's like nothing. Well, it's 1, but it goes away because it's multiplied by 1. So really, I just want 3 to the 4th power. That would be 81 p to the 4th. 3 to the 4th power is 81.
Would you not distribute the 4 to the 3 into the p individually, or do you just have to combine them both?
Ask your question one more time. I didn't understand it.
Would you distribute the 4 to the p individually to the 3? Or?
So yes. So when you have something that looks like this, because it's a monomial, there's not a plus sign in it. You can do where the 3 is multiplied, or the exponent of 3 is multiplied by 4, and exponent of p is multiplied by 4. So it's 3 to the 4th, p to the 4th. So then I have this number, and this number that I'm multiplying together. 1 times 3 to the 4th times 2 to the 0 is 81. Let's do one more before I let you keep trying. So this next one, because again, the x term has a variable, we're going to be multiplying 4 times 3 cubed times 2 to the first power. 3 cubed is 27. 27 times 4 times 2 is 216. And then you have p to the cubed, p to the third. Do we see it now? Can you finish simplifying this out?
Maybe.
Maybe. I like the maybe. We'll take the maybe. Okay, I see some confused faces, so can we put those confused faces into questions?
Wait, hold on. Where's my calculator?
Did you get something there?
No, I got the same, but I don't know how it ended up being the same. 216.
The 216 times 216?
Yeah, I was that.
Pure luck. No, yeah. Just happenstance that those are the same coefficients. Okay.
My math's wrong.
My math is wrong. That's okay. All right. Cool. So we have now had an example where the first example just had a number for a, and the first term in that binomial was just a single x. The second example has both an a value and a coefficient for the x term. This is the more complicated problem. On the back page, we have one more example using the binomial theorem, but this time, what do you notice about the problem we're going to do in example 4? Are there any numbers at all? Not really. We just have exponents. We don't have any coefficients. Actually makes the problem easier. Okay? Stick with me. What's the n value? 5. So that means Pascal's triangle is going to be what number? Yeah, 1, 5, 10, 10, 5, 1. Those are going to be the coefficients for each term. The first term decreases. The second term increases. So if we are trying to do x to the third plus y to the seventh all raised to the fifth power, we pick the Pascal triangle number, the first term to the most power it can be, 5, and the second term to the least power it can be, which is what power? 0. Then we just keep going with this series, adding Pascal's triangle number that comes from the combination, decreasing the x cubed power, and increasing the y to the 7th power. So my next term would be what? 5 times
X cubed to the 4.
Times.
Y 7 to the 1.
Yes. See, we're decreasing the x cubed and increasing the y to the 7th. My next term would be 10 times x cubed to the third times y to the 7th raised to the second power, plus the next term in the series is 10 times x to the third to the second power times y to the 7th to the third power. Still making sure those powers add up to 5, which they do. And then I have 5 x to the third to the first power, y to the 7th to the 4th power. And then last but not least, we have Pascal triangle number 1 times x to the third to the 0 times y to the 7th to the 5th. I'm going to let you guys simplify this one. My gift to you, you get to simplify this one. I'll give you some time. Here we go to check our work. We should have x to the 15th plus 5x to the 12th, y to the 7th, plus 10x to the 9th, y to the 14th. plus 10x to the 6th y to the 21st plus 5x to the 3rd y to the 28th plus y to the 35th.
Oh, okay. I did something, I did a silly.
You made a silly?
Yeah, because I thought it was you have to add the extra ones to multiply them.
No, when it's a power raised to a power, you multiply.
Yeah.
Yeah. It's when the bases match, that's when you add the exponents. When it's powers raised to powers, you multiply. We're going to use the binomial theorem to find the coefficient of x to the 4th in the expansion of plus 3 to the 11th. Now, I'm pretty sure we don't actually want to do something to the 11th power. Do you agree? No, I don't want to do anything to the 11th power, even using the binomial theorem, because that's wild. So instead, we're going to use the formula in this series for the binomial theorem to find just one particular term. What I mean by that is we're going to use the formula n choose j times x to the n minus j times a to the j to find that particular term. That's from the front of the notes. I didn't just make that up. We have to figure out, though, what j is. The way that we do that, to find j, we know that x to the 4th, given in the problem, is going to be equal to x to the n minus j. But n is 11. How is n 11? Where did I get the 11 from? Yeah, the problem right here, yeah. Which means if that needs to be 4, what am I subtracting from 11 to make that 4? 7. So I know that then n is equal to 11 and j is equal to 7. That is everything that I need to fill out for a particular term in the binomial theorem. I would plug it into that formula. We are doing n choose j times x to the n minus j times a to the j. What's a? Well, it's a vowel. Come on, man. What's a? 3, because it's the number in the parentheses. So times 3 to the j power, which is 7. We don't need to expand the entire binomial theorem to find this term. We can just pluck out a single part of this series if we know all the parts, which we do, n and j and a. Okay, so in your calculator, do you guys remember how to do n choose j? Oh, flip back to the front of your notes. N choose j has a formula, but I'm going to teach you something even quicker than that so you don't have to use the factorials to find it. There's actually a button on your calculator for n choose j. Everybody in their calculator, type 11. Then you're going to click math. You're going to toggle over to the probability menu, PRB, probability. And I believe it's option 3 where it says n choose r. Is that what it says? Great. You've typed in n already, so it says 11. And then you're going to choose how many? 7. So type 7, let's press enter. What did it give you? 330. That's n choose j. That would have been the number in the Pascal's triangle had we multiplied Pascal's triangle enough times to get to n equal to 11. Don't recommend it. Numbers get really, really big. This is going to be times x to the 4th power multiplied by 3 to the 7th. Ooh, what is 3 to the 7th power, please? It's a big number. I didn't know it off the top. 2,187. Now to get the final coefficient of x to the 4th in this expression, I just need to multiply those two numbers together. So 330 times 2,187 is 721,710 times x to the 4th. But I just want the coefficient, so I just want this. Yes, sir.
Where did we get the 2,187?
It's a great question. Where did anybody answer that for him? Where did we get 2187 from? 3 to the 7th. So we had n choose j, which was the 330. X to the 4th was this. And then 3 to the 7th was this part. And then we multiply the choose number, the combination, and then the power of a together to get the coefficient. Now notice it asked for the coefficient, not the term. So it just truly wanted the number here in front of x to the 4th. There's a different way to ask this question when it wants the whole thing, which is what's happening in the next one. It says use binomial theorem to find the 6th term. That means I want the exponent in everything. So not just the coefficient on this one. I want the entire 6th term. For this one, though, we have to kind of work backwards a little bit. We don't know what power the 6th term is. So if we list it out, 1, 2, 3, 4, 5, the 6th term, which is what we want. What would be the first power in this sequence? It would be x to what power? To the 8th, yeah, to the n power, to the biggest power it can be, 8 coming from here. Which means the second term is going to have x to what power? And then x to the 6, then x to the 5, then x to the 4, then x to the 3. The reason I need that is because I need to know the power of x for that particular term. Now, we can do this exactly like we did the problem before this. If we know that x to the 3rd power is going to be sum n minus j, x to the n minus j, and n is 8, what is j? 5. Where did I get the 8 from, by the way? The original problem, yeah, the exponent of the binomial. So we know that n is equal to 8 and j is equal to 5. Let's fill out that binomial theorem formula from the series itself and just calculate that 6th term. This would be n choose j times x to the n minus j times a to the j. What's a this time? -3. Very good, because we have -3 in there, the a is going to be -3. Can you guys figure out that final term for me? You can use the formula with the factorials to do 8 choose 5, or you can use the shortcut in the calculator. I'll give you some time. So the 6th term, when we do 8 choose 5, we get 56. 8 minus 5 makes the power 3. And -3 to the 5th is -243, which means the 6th term, if I were to do all 8 terms of this expansion, would be -13,608 x to the 3rd. Things we don't want to do by hand. Luckily, we now have the binomial theorem to do quicker for us. Okay, so I have given you guys a very short classwork assignment that needs to be turned in before you leave. There are 8 problems on it, and 4 of them are about combinations. You can use the shortcut I just showed you in your calculator to check your work, but I want you to show me the formula first with the factorials whenever you're doing that. Then you can keep going.